So in this video, I want to talk about two different ways that we can set up our material balance equations and eventually solve them. And the two different ways, so again we're hitting on material balances again, but the two different ways, one involves flow rates of individual components, and the other involves mass or mole fractions. So let me just draw an example here where I have a separator, where I have one stream coming in and two streams coming out. I'm going to label this stream 1, 2, 3. And I'm going to define the overall flow rate, F, and then G, and H. So F, G, H, overall flow rates. And that can be in terms of mass or moles. So the units would be mass or moles. So we have the amount of mass coming in, or the amount of moles coming in, and we have it leaving, but this doesn't tell us about individual components. And what I mean by that is individual chemicals. So F over here, it may be a solution. It may be a solution of water and salt. It may be a mixture of toluene and benzene. It may have 3 components or 4 components. It may have ethane, methane, butane, various components, whatever it is. And if we know the overall balance, that's great, but it doesn't tell us what the actual composition of these flow rates are. And there's two different ways that we can do them. One is what I'll call the component balance, where we write out the individual variables for the different components, and we can set up material balance equations for them. So let me talk about the first method, the component balance method. And this is where we go ahead and define individual variables for each of the components. So let's just assume we have, in this example, we go ahead and have 2 components. And in this case, let's just take the example of benzene and toluene. So we have a mixture of benzene and toluene. And I can define the following variables. We'll call this B1, B2, B3, T1, T2, T3. And these variables that I've defined, and they can be anything. They don't have to be B and T. I just chose benzene and B and T because they match benzene and toluene, but they can be any sort of variables. And in this case, B1 just represents the flow of benzene in this first stream. B2 represents the flow of benzene in the second stream. B3 represents the flow of benzene through the third stream. And the same with T1, T2, and T3. And I can go ahead and write overall balances here. B1 is equal to B2 plus B3. And then T1 is equal to T2 plus T3. And that now we have the variables defined. If this was a real problem, I'd want to make sure that I go ahead and write out my variables here on my flow chart, my block diagram here. I'd write, B1 here, B2 here, and B3 here, same T1, T2, T3. I'd make sure that those are properly labeled on my flow diagram, and from there I could go ahead and set up these equations. And let me just write down here, I forgot to write the total balance. F equals G plus H, but I have 3 equations here, and I can go ahead and solve the system to get any unknown variables that I may have. So that's one method, the component balance method. Let me talk about the other method, which involves mass or mole fraction. So let me just quickly redraw this. This is 1, 2, 3, and this is F, G, H. And so, again, F is equal to G plus H. Well, now we're going to talk about the mole mass fraction method. So each of these streams here, we can also define, write out variables for the mass or mole fractions. So again, let's look at the example where we have benzene and toluene within a mixture, two-component mixture. And we oftentimes will use W for mass. I can write that out. And we use X for moles. So in this case, I can write out WB1, and that would be the mass fraction benzene in stream 1. And I could write WB2, WB3, so those would be the mass fractions in streams 2 and 3. I could also write out alternatively XB1, XB2, XB3, which would be the mole fractions. So there's a relationship between mass and mole fractions, and depending on what units we're using for a problem, we may work out the problem in terms of mass fractions or mole fractions. And this is not all. There's also the mass fractions for WT1, WT2, WT3, and then we have XT1, XT2, XT3. So these again are the mass fractions of toluene in the various streams, and then the mole fractions of toluene in the various streams. And now we can go ahead and set up some equations for this system in terms of material balances. Let me just shrink this down and move it up. So before we would just write the amount of toluene going in here is equal to the amount of toluene here plus here. Well, we're going to do the same method, but in terms of molar mass fraction. So let's look at mass first. And let's do mass balance on B for the benzene. So in this case, F times WB1 is equal to G times WB2 plus H times WB3. So this is the mass balance on benzene. So the total flow rate here multiplied by the mass fraction, that tells us how much benzene is flowing through this stream right here. So if the mass fraction, for instance, is 0.5, then 50% of the total flow rate is benzene. So 0.5 times the total flow rate would tell us the amount of benzene flowing through here. So the amount of benzene in stream 1 is equal to the amount of benzene in stream 2 plus the amount of benzene in stream 3. So that's just simply the mass balance. We can write out similar equations for toluene. And you may have already guessed it, WF times WT1 is equal to G times WT2 plus H times WT3. And there we have it. We have mass balances on benzene and toluene. And if some of these were unknown, we could use these algebraic expressions to go ahead and solve for them. Let me just shrink this down. And lastly, we have mole fractions. And I'm just going to write out all these balances here. F times XB1 is equal to G times XB2 plus H times XB3. So in this case, F would represent the mole flow rate. So if we defined F in terms of mole flow rates, then we would use mole fractions, just like I've shown here. On the other hand, if F was in terms of a mass amount, then we would use these equations up here. So it all depends on what units we have. If we're given that F is equal to, say, kilograms flowing or grams, then these are the equations we would use. We would solve it in terms of mass fractions. On the other hand, if F is a mole, say 25 moles or whatever, this is the equation we'd use. And of course we have F times XT1 is equal to G times XT2 plus H times xt3. So those are the equations for the mole fractions, the mole fraction mass balances. Now we have one other thing that I just need to remind you of, and you've seen this before, but it's important to keep this in mind, that mass fractions and mole fractions are not independent. The sum of all mole fractions in a stream equal to 1, and the sum of all mass fractions equal to 1. So in this case, let me just put a nice little box around that. In this case, xb1 plus xt1 is equal to 1. xb2 plus xt2 is equal to 1. And if you haven't figured it out, xb3 plus xt3 is equal to 1. And I could also write out the mass fraction equation, wb1 plus wt1 is equal to 1, etc. And then I could write them for streams 2 and 3. So if we know, for instance, we know b1, we will by default use this equation to find out what t1 is. So oftentimes we don't need to write out all of the mass balance or mole balance equations because of these relationships. As soon as I know xb1, I know what xt1 is because of this relationship. As soon as I know xb2, I know what xt2 is from this relationship right here. So when you're solving a problem, you just have to choose a method you're going to use. You can solve it again by writing out the problem in terms of molar mass fractions, or you can write it out in terms of individual components flowing through the material. So again, if I was going to write this, solve this problem and write it out as a flow diagram, I would write out my variables on my process or my block diagram, and I would either write those individual component flow rates, or I would write the mass or mole fractions right there, and then so I would have a clear understanding of what all the variables are involved in this problem.